Hello and welcome back to another chemistry tutorial with me, Miss T. Today we're going to be looking at the ideal gas equation. This is covered in all A-level courses as well as IB, topic 1, so that's SL and HL. As usual, we'll start with some definitions, go through some worked examples, and then finish with some practice questions. So we're back with Avogadro again as we measure the amount of substance in moles, and there are 6.02 times 10 to the 23 particles in 1 mole. So far, we've looked at how we can relate moles to mass, moles to concentration, and moles to gases when we're dealing with one particular temperature and pressure. But for the ideal gas equation, with the ideal gas equation, we are calculating moles at a number of different pressures, temperatures, and volumes. And so we use this expression here, PV equals nRT, where P is pressure measured in pascals, V is your volume measured in meters cubed, N are your moles measured in moles, R is your gas constant, which is 8.31, and your temperature, T rather, is temperature measured in Kelvin. We need to be able to rearrange our ideal gas equation to make the subject whichever the quantity is that we're trying to calculate in that example. So to make P, V, N, or T the subject of that equation. Now, the most common mistake made in ideal gas equation questions is students not putting each quantity into the correct units. So remembering that pressure must be in pascals. Often in questions, they'll give it to us in kilopascals. We have to multiply by 1,000. And volume having to be in meters cubed. Often in the question, we're given the volume in centimeters cubed. And so to convert, we have to multiply that by 10 to the power of minus 6, which is the same as dividing by 10 to the power of 6. Or if it's decimeters cubed, we multiply by 10 to the minus 3, which is the same as dividing by 10 to the 3. For Kelvin, if we're given temperature in degrees C, we just simply add 273 to get our temperature in Kelvin. So for our first worked example, if we want to calculate the number of moles of a gas at a temperature of 60 degrees C and a pressure of 250 kilopascals, occupying 1,100 centimeters cubed. So before we try to put any of these quantities into the ideal gas equation, we need to first make sure that everything is in the right units. So pressure multiplying by 1,000 to give us 250,000 pascals. Volume multiplied by 10 to the minus 6, or dividing by 10 to the 6 to give us 1.1 times 10 to the minus 3 meters cubed. R is always just given to us in the question anyway. And then T converting to Kelvin by adding 273 to 60. Now, if we continue on with that same question and actually calculate the moles, well, now we've got all of our quantities in the correct units. So we can rearrange our ideal gas equation to give us moles, or N equals PV over RT. We then simply substitute our values in, and we end up with a value of 0.099 moles. Again, continuing on with the same question, let's say we've calculated the moles, but the next part of the question is asking what is the MR, or the relative molecular mass. So if they've given us the mass as 1.60 grams, we know that MR is equal to mass over moles, so that will give us an MR of 16.1 grams per mole. If we take this question even further, and for that gas we're asked to suggest the identity, then we'll use the periodic table to try and determine what is the identity of this gas that has an MR of 16.1. So our first instinct might be to go to oxygen with a mass of 16. However, we know that oxygen doesn't exist as individual oxygen atoms. It exists as O2, which would have an MR of 32. So it can't be oxygen. So our next option might be to go back in the period table a little bit and go to nitrogen with an MR of 14, and then make up the last two with hydrogens, so NH2. But again, we know NH2 doesn't exist as a gas. We would have NH3 as ammonia. So it can't be that either. So if we go one further step back and we've got carbon with an MR of 12, and then we add four hydrogens, which gives us CH4, that is the very well-known methane gas. So that is the correct answer. It's now your turn to use the ideal gas equation in the following examples. Pause the video now and press play when you're ready with the answer. So for our first question, just making sure that all of our quantities are in the correct units. So for our pressure, making sure that those are in pascals, volume in meters cubed, and temperature in Kelvin. For our next question, 0.140 moles of a gas has a volume of 2.00 decimeters cubed at a pressure of 90.0 kilopascals, and we're calculating the temperature. So we can rearrange our ideal gas equation to make temperature the subject. Temperature equals PV over NR. Now, before we put anything into our new expression, we're going to make sure that all of our quantities are in the correct units. So pressure in pascals by multiplying by 1,000, volume in meters cubed by multiplying by 10 to the minus 3, moles, just moles, and R is just R. So we can now put that into our expression and we end up with 155 Kelvin to 3 significant figures. For our final question, at 273 Kelvin and 101 kilopascals, 6.319 grams of a diatomic gas occupies 2.00 decimeters cubed. Suggest the identity of the gas. For the identity, we know we're going to need the MR, and to get the MR, we know we're going to need the moles. So moles equals PV over RT. As before, we'll make sure that everything is in the correct units first, and then substitute that into our expression to give us 0.089 moles. MR is mass over moles, and so we end up with an MR of 71.0. In the question, they've told us that this is a diatomic gas, which means that there are two atoms bound within that molecule. So 71.0 over 2 is 35.5. So we must have two atoms of mass 35.5, which is chlorine. So our gas is Cl2, chlorine gas. So how did you do? Let me know in the comments, and also if there are any other topics that you really want a mini tutorial on, please let me know there as well. See you next time. Bye.